Hey team. Just a second, gotta pour myself some coffee. It's impossible to teach calculus without some coffee. Yep. Nice. How's everybody's weekend?
Good. How about you?
Yeah, good. Had a friend that has motorcycles, and he said he invited me to ride with him because I just borrowed one of his, and it was a blast. I felt on the edge of destruction the entire time because it's been a long time since I rode, but we ripped around up on the Jacksonville hills up there, and there was a minimal number of crashes, so it was a blast.
Yeah, those are too scary for me.
Last week before finals week.
Isn't that a trip? It's exciting. You only have through one of the things I'm really happy about with respect to our schedule is you have a test on Wednesday, which means you kind of don't have to do anything for Thursday, Friday, Saturday, Sunday. You sort of get some time off, which is awesome. So that worked out good. All right, I want to start off with just a quick look at the project, because as I've said before, my goal for these is not to have something to put in the grade book, but to teach you something. So many of you may have got this question right, so I'm not going to spend a lot of time with it, but I only started grading it like, I don't know, 30 minutes before class. So I got like 5 of them done. So I'm not very far into it. But I just want to show you some of the thinking behind it and also show you some good looking answers so that you grow, so that you get a little bit better. Also, I'm not going to limit myself by choosing a value for R, because I want to show you something that's kind of surprising, if you will. Let's see, how do I get rid of that? Recent notes. That works. And interrupt if you have any questions, but I just want to show you the process by which you could have got this right. So given that you are trying to maximize the volume of a cone, then this is your governing equation. So that's what you're trying to maximize. But as I said, what's interesting about this problem ultimately is to make one of these things, you actually have to start with a circle and come back and chop a chunk out of it. So I might go right there and say, chop this chunk out of it. And so the only thing you really have, if you're going to make a cone, there's only a couple things you can touch. One of them is what size is the flat circle that you're cutting out on the ground. And the second is, what is this theta? And I was telling you, it makes your life a little easier if you think of the larger angle as theta. Although if that angle was 300, you'd probably go, oh, 300 minus 360 is 60. So I'll cut a 60-inch sector, a chunk out of it. And so that's the only thing you can actually touch. Like, you don't have a radius and a height. They don't exist yet. And oddly, as soon as you kind of take these two edges right here, now that this part in the center is gone, and you push them together, like, you're just stuck with the radius. The radius just happens as a result of your choice of theta. And it happened, and the height happens as a result of theta. And so that's why I said ultimately this problem, the first step is to figure out what V as a function of theta is, because that's the only thing you can touch. It doesn't really do any good to say I know what R should be, because I don't have R until I've actually chosen theta. So I hinted at the fact and left you with the understanding that that arc length right there, S, I told you or reminded you that if you take the radius times theta, that will give that to you. And since that value, once you actually turn this into a cone, since that value actually ends up over here, in other words, that ends up right here, and since that circumference is equal to 2 times pi times r, that's in a sense also what S is. And so putting that together, you can say that 2 times pi times the radius has to equal r times theta. And so r is equal to r times theta divided by 2 pi. Most of you left class discovering that. And remember, capital R is a constant. You did not necessarily notice this because I told you to pick a number for R because I didn't want you to be confused by this. But what I'm going to show you here that's kind of cool is you don't even have to choose capital R yet. You can wait till later, but you have to treat it like a constant. And so then I can say, if that's true, then I can come over here to my velocity and I can replace, I still have the 1/3 pi, but I can now replace R with R times theta over 2 pi. So there's R squared. Now I just need H. How am I going to get H? Well, and I left you with most of these hints. Given that this distance down here is R and that height there is H, and this slant height R over here shows up right there, then you can also say that R squared plus H squared, oops, that's plus, would have to equal capital R squared. And so I can solve that for H by subtracting the little r squared over and then square rooting both sides. And so there's what H is equal to. So now I have all the ingredients that I need. So then if I replace that with H, so I'm just replacing my H up here with what I just discovered. So that's the square root of R squared. And then instead of R, I'm going to replace R with what it is. Then you now have the volume just from picking theta alone, which is really cool. Now I want to show you something kind of neat. If you go over to Desmos, and it's something I'm constantly kind of trying to get you to believe or to understand. But if I go over to Desmos and I graph this, now you might notice for a second here that what I have typed there is not what I just showed you a second ago. Well, remember, what I have to do algebraically to get the answer to this is I have to take its derivative. And so I'd like to clean that mess up a little bit. And so what I've typed there is that mess algebraically cleaned up a little bit. I'm going to have a lot easier time taking the derivative of this statement that I have here than the statement that I had just written a second ago. And so notice my radical sign doesn't have a fraction in it because I factored stuff out. I cleaned all that mess up. So here's what's really cool about this. Notice that for my example of radius is 2.5, I'm done. Like, you don't need calculus. There isn't that point the maximum point because of the technology in the world in which you live in, literally doing the calculus. If your goal was I'm a product designer, I'm making stuff, then you're done right now. You don't do calculus just for the fun of it. You do it when you need it, and you don't need it because you have technology. And so notice for my example, when the radius is 2.5, the capital R radius is 2.5, I got that the angle that I need to cut here, theta, is 5.13, because that's kind of my X over here, right? And when I do that, I get a volume of 6.298. Like, that's the biggest volume cone I could possibly make. Just as a side note, that angle, because it's in radians, in degrees, is like 294 degrees approximately. So that means, let's see, 294 minus 360, 66. That means if you cut a 66-degree angle out of your circle, that would be the best choice. Watch what happens if I change capital R to other numbers, though. Notice it doesn't even make any difference. No matter what.
Sorry, can I go?
Answer. Go ahead, Eve.
Isn't that because, at least this is what I found when solving it, when you take the derivative, R disappears?
Yeah, it has to do with the fact that when you take the derivative, R ends up out front. Notice the business end of even the equation right here has a theta squared times the square root of another expression with theta squared, and the R can be thought of as out front, like out there among the constants. And so it ends up having no effect on when this is equal to 0. And so you're exactly right. It actually kind of cancels out in this solution. And so you wouldn't have necessarily noticed that because I didn't want this problem to be too hard. I purposely told you start by picking capital R as 8 or 10 or 12 or whatever. And so you wouldn't have had this expression, but it's just kind of cool to leave this problem noting that it actually doesn't even make any difference what R is. And if you think about it, it kind of makes sense, doesn't it? I mean, you know, if it gets bigger, it's not obvious, but if you chose a larger radius, isn't it still proportionally a circle? And so if I cut the same angle out, isn't it gonna not make any difference whether it's a large or small circle? Maybe you kind of go, oh, I guess that does make sense. But if you did the algebra, just again, treating capital R like it's a constant, it ends up canceling out of this problem, which is rather cool. And so I only want to show you just a little bit more about this, and we'll say we've learned enough there. Because I'm not going to go through the entire process. But I think what's important about that is you have this equation, you graph it, you now know the correct answer is 5.13, which is why I told you in the second question was to, you know, graph it, like put it in Desmos and graph it, because you know the right answer right now. And so now when you proceed to calculus, where you take the derivative of that statement and you set it equal to 0 and solve it, you're sort of hoping, well, I better get theta's 5.13 or I kind of screwed it up somewhere. So that's kind of neat to know. And so it's a cool, powerful feeling, I think. I hope you feel that I don't need to rely on the graphing calculator to get this answer. I actually know calculus and I can do this algebraically. There's some cool points to that, even though, as I said, in the real world, you're done. 5.13 is the answer. But I also want to illustrate, and I'm just rewriting what you saw in Desmos a second ago, but if I rewrote the derivative equation as r cubed over 24 pi squared, and I think of that as a constant out front because that's what it is, and what's left over here was theta squared times the square root of 4 pi squared minus theta squared. And so taking the derivative of that statement is going to be a lot easier than taking the derivative of this statement up here. That's terrifying. There's just lots of numbers everywhere. So by pulling all the constants out front, I can just ignore those. And so when I say, okay, what's v prime of theta? Well, I can just stick this answer down here, 24 pi squared, and then I can go worry about the derivative of this. What are you thinking when you see that statement up there? If you want to take its derivative, yours doesn't necessarily look like mine, but what do you see there? What rule governs what I'm doing there?
Product rule.
Product and chain.
Yeah, product rule, ultimate product rule initially, and then the square root of junk is also going to include chain. And so that's a legit, I mean, that's why this is such a kind of a cool problem. It's amazing that you sort of need that much calculus, like you need all those rules, product and chain. I guess I'll go ahead and write that in there too. And so then I have this mess down here. And again, whatever mess I get, and that's going to be a giant mess. The question is, can you algebraically clean that up a little bit in order to get the final answer? The exact answer to this question, although approximately 5.13 works out to be exactly the square root of 8/3 times pi if you pull the pi out. So to me, first of all, just given the fact that, you know, a cone is made from a circle, it's nature oftentimes is just so exacting and so beautiful. I just find it so weird that the answer to this is such a weird angle. It's not a nice, neat degree, and it's not a nice, neat radian. You know, this number right here is irrational, and it's multiplied by, well, pi, which is also irrational. So this is like as irrational as a number could possibly get. So the reality is you can't actually make the perfect cone because there's no way to measure something that accurate. It's impossible in a theoretical sense. Practically 5.13 is plenty close enough. Or as I said, 294 degrees, close enough, you know, that's kind of cool. So maybe you survive all that. And again, you're more than welcome to discuss with me after class, like where you went wrong, or, you know, have me show you some of the details or fill some of that in. But I also want you to realize that, you know, part of this is a neat problem. And if you get it right and you want to turn and then present it to somebody, I just want to show you what I meant. So I said, part of your grade on this is presentation. Like, can you actually present this in a pleasing way that will actually make somebody want to read it? And I said clearly on my sheet, I'm talking magazine article quality, not just orderly mathematics, but like make somebody want to read it. Can you do that? That's a neat skill to have. It's not really part of this class, but it's a neat skill. So I'm thinking of it as being like you got to get an A, you got to have presented it nicely. Again, I haven't waded into very many people's, but let me just show you a couple of things here. So in order to grade it, I quickly typed everything out. And so I would say this is not magazine quality. It's good in the sense that I have step 1, I told them a little bit, here's how a cone is built. Step 2, let's find this function. And I made I have little I, and then here's where I found R, and then double I, here's where I found H. And then I put it all together and showed a couple of simplification steps. And there's my nice, beautiful, bold red answer. Like, that's good communication, but it's not very engaging. Like, people don't necessarily want to look at it. And then I graphed it, and that's kind of nice. And then I took its derivative. Notice I showed 1, 2, 3, 4, 5 steps till I got a derivative that was algebraically simple enough that then I set it equal to 0 and solved it. And so that's very clear, but it's not very exciting. Would you agree with that? I've only graded a few of yours, and so I'm going to brag on Cheyenne's for a second because she went over the top with this. I hope you don't mind, Cheyenne. But it's like, that is freaking awesome. Good job. I mean, and I want to highlight 2 things. Number 1, that's engaging. Like, there's boxes in different places. Like, that looks a lot more fun to read. If you have mine and Cheyenne's to look at, you're going to look at Cheyenne's, not mine. Having said that, just because it's beautiful, does that make it right? No. Like, it's more important to get the math right. If Cheyenne got it wrong and mine was right, mine's better than Cheyenne's, because we're trying to, change the world, build something accurately here. And so looking nice is no substitute for being correct. So I want to, highlight that. But the cool thing about, Cheyenne, I don't know where maybe you can say something about this, Cheyenne, but she's heard of something called a pizza cone. So it's kind of like, here's your flat pizza crust laying here. And the idea behind a pizza cone, apparently she fixed pictures behind it, but it's like if you chop a chunk out of it and then you fold that dough into a cone, now instead of your pizza just having ingredients on a flat surface, now you get to fill the entire cone with stuff. I mean, I'd love to see you try to eat that, Cheyenne. But that adds some fun to it, doesn't it? I mean, that's kind of neat. But the thing I really like, I guess, is just the fact that, notice how she's got like blue boxes with some of the stuff in it. So it kind of breaks it down. When you look at mine, it's kind of, it's just one of those bunch of equations staring at you. It's like equation, 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 equation. It's accurate. It's not wrong. And it's nicer looking than pencil, right? So, to me, mine's mine's a B. It's like it's there.
I just want to say the graph on that, when I fixed the volume equation, I didn't update the graph, so that's actually showing a volume of like 619 cubic inches, which is way too high.
Yeah, because Cheyenne screwed up. Like, she thought the equation was pi. What did you say it was? What did you do wrong? You forgot the third.
I used pi r squared times h.
The volume was wrong.
Yeah, so I fixed that and sent a different version. And I have a one with the correct graph in it as well.
Oh, you don't need to send it to me. Yours is good. So on a simpler level, let me just show you something I was playing with after my last class. So these are just skills with word that you want as an educated human being. Again, this has nothing to do with math, but I'm trying to get you a job here, not just make you good at math. So I'll show you what I did to get these. And so that's better. Now, that still isn't awesome, but at least it's kind of like broken into things to pay attention to. And I got it to fit all on one screen. But for the sake of your larger education, I just want to show you how that's done, just because it's really easy to do in Word. If you've never seen this before, it's worth your time just to take a couple of seconds. If I go over here and I say insert, there is something called a text box. And so I'm inserting a text box. And notice it kind of wants to move, but not really. So then what I can do is go in here and grab all this stuff. Actually, I'll grab I'll move it up there. I can go grab all this stuff over here and say copy and go into this text box and say paste. And there it's all in that text box. And now I kind of don't need that anymore. And so that's still pretty boring, but could you then go back and do a couple things to it? Like if you click on it and right click, you can format shape, or up here, it's already highlighted just because I clicked on it. It wants to highlight that. And notice you can do a shape fill, which I can say, hey, I think I'll fill that shape just to make it look a little more interesting with kind of a light blue color. And you can outline it with borders and make it all cool and stuff and go crazy with it. And then if you right click and go down to format shape. No, that's where I already went. Sorry. That's the same thing I just showed you a second ago. If you right click and go to wrap text and say tight, watch how this thing behaves now. And this is what I mean when I say magazine article. Watch what happens when I put it amidst all these words. Do you see how the words go around it like a magazine article? So if I did want to type around it, I can sort of move this thing around, and whatever words I have typed, it moves around inside all of those. And so, and then of course, just colors help. Like mine has gobbledygook, but at least I have highlighted here, you know, in red bold letters, like the result of all of this. That's kind of cool. And if you want the title to stand out, you know, just coming back and making it bold and making it a little bit bigger. And maybe I look at this and think, yeah, that's cool, but it should be bigger too, because that's, you know, the final answer. I want that to stand out. I mean, my point is, doesn't that look better? Like it gives me something to look at. And if I can sort of make a progression of some of those, maybe I can make this, you know, look a lot better without a whole lot of effort. I just think that's worth something. Keep in mind that, you know, when you discover something cool or when you make something interesting, you've got to communicate it to other people in the real world. Like you might want to build a bridge and come up with a great design, but you're not going to build the bridge alone. Like there has to be people that put money into it. There's government people that have to vote yes. There's workers that have to be able to read what you do, your design. And so you got to sell that whole thing. And so part of, like, it's good if you're smart. That's awesome. But a chunk of that, a chunk is being able to communicate your thoughts to other people. And so, you know, did you spend any time at the top of this introducing like what you're doing, or did you just jump right into math? I mean, that's what you're used to doing because you're just communicating to some dork like me that gave you a problem. But, you know, if you're presenting it to somebody else, they don't even know what you're talking about. Like, did you spend a little time drawing some pictures and, you know, showing them, like, you know, so that they go, oh, okay, so yeah, if I make a big cut, then I get a tall, thin cone. If I make a skinny little cut out of it, then I get a low, wide cone. You know, do they have any, does the person reading, does your reader have any sense of the problem? And then, you know, then you proceed into all the math that produces the correct answer. That's kind of cool. So again, I show you this because I want you to grow. And also, you know, like there's people that are really artistic. Maybe Cheyenne's one of them. Maybe you did a good job with this too. I'm not one of those people. I'm not super artistic, but you don't have to be, you know, real artistic to at least do a little bit better. So the text box idea, I think, is kind of cool. And I showed you before you left how not only can you insert a text box, but you can insert an equation so that the stuff is all typed out and readable instead of just doing it in scratch work. It's very rare that you need to do anything that's not just scratch work, at least for a regular class, but you would never have scratch work in the real world, right? It would always be something presentable. So, you know, it'd be a bummer if you left college not being able to do that. That's why I included that as a tiny part of your grade. It's like 2 points out of 20 if you just turn in a bunch of ugly scratch work. One of them that I graded was just a bunch of kind of a scratch work, but their work was awesome. Well, they still got 18 out of 20. You still got an A. It's still a math class. But I just think it's worth thinking about. Any comments on that? Thoughts?
I had fun.
Yeah, I'm glad you had fun because I certainly didn't want it to be work.
I like this project a lot more than the last ones.
Good job, Cheyenne. Thanks for not taking offense at me sharing your work. Since I never asked, I just did it. Okay, I got something cool to show you today, and so let's get after it. And this is, I don't know if you noticed this, but this is the last thing you actually have to learn in this class. From now on, we're just kind of landing the plane, taking some tests and showing what you know. But this topic is something called, I need to share screen. Actually, it's something called Newton's method. And again, I think it's kind of fun to add a little context to this. So rather than just showing you Newton's method, I'm going to show you Newton. Because I find this kind of interesting. And there's not always time to do this in a math class, but there the dude is. Check out the sweet hairstyle. Born 1642. These are the dinosaurs without Desmos and so forth that figured all this stuff out. But Isaac Newton in particular was one of the two people credited with inventing calculus. Somebody had to figure this out first, and Newton invented it along with a guy named Leibniz. And but he was not just a calculus inventor, and so amazing person. Another great mathematician named Lagrange, that's how you pronounce his name, described him as the greatest genius who ever lived. That's an amazing statement. But I teach in
Were you just skipping
engineering.
over Euler?
Go ahead, Vale. What'd you say?
Were you just skipping over Euler?
Yeah.
That guy invented so
argument,
many
I don't know
things
how
that
you
they had
know
to stop giving him credit.
I'd say there's a definite argument that Euler, you pronounce his name Euler, E-U-L-E-R, Euler was greater. He was more prolific than Newton. So awesome observation. But I teach engineering 211 and 212, winter and spring, and that's statics and dynamics. Some of you said you're going to be an engineer, and you'll probably have me for that class next year. But the entire subject of engineering hangs on Newton's laws of motion, which if you've taken physics or will take it, the whole hall of physics kind of hangs on those ideas. I love this. There's a couple of things I love about him, and this is one of them. And I haven't read very much. Like you can tell, this is a Google search, and I stole most of this stuff off of. It took me 10 minutes to find this. It's not like I've read books about him or anything. But I love this. He had a rather modest view of his own achievements, and he wrote in a letter that if I've seen further, it's by standing on the shoulders of giants. Like, what an awesome, humble guy to be somebody this great and yet credit people that, got him to that place instead of just saying he was awesome. That's not something you see too much today. And I love this statement too. I don't know what I may appear to the world, but to myself, I seem to have been just like a boy playing on the seashore and diverting myself now and then, finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lays undiscovered in front of me. He's like, he found some amazing things relative to other people, but he realized I'm just scratching the surface of all the things that are out there. But laws of gravitation, he's the first person that ever built a telescope, or at least a refracting telescope. There's something called the law of cooling that you may have seen in an algebra class. He figured that out. Studied light a lot, like the diffraction of light, and how maybe you've seen that where the light passes through a prism and it turns into this spectrum of colors. Like he spent a whole bunch of time with that, and just a very, amazing guy, amazing person. Anyway, we're responsible. We are thankful to him for this. And so let me show you this right now. Let's use it. In your graphing calculator, you would have done this in Math 111, and Desmos is better at this than your graphing calculator, but let's use the graphing calculator as a tool, since you've probably seen that before. Let's see, why are you not opening? Oh, he is trying to open. I'm just not being patient. I think I opened the calculator 4 times because I'm impatient. So I have this equation sitting in my calculator from, well, I think it was from last week when we studied inflection points, or I don't know, I forgot when we studied it, but there's the graph of whatever, some crazy equation. And you may remember that we in Math 111 found the zeros of a function. In other words, the x-intercepts. You can see for sure it has one right there. It looks like between 1 and 2. And remember, finding the x-intercept of a graph is not really the point here. The point is, well, we just saw it in that project. What if you got an equation that was so huge and you set it equal to 0 and said, wow, I either don't want to solve that, or I can't solve it, or no one can solve it. You can always solve any equation by cheating. If you have ugly equation equals 0, then you just type in ugly equation equals y, And then you look for, well, the zeros, you look for that place where it crosses. And so there's a lot of equations that come up. I have a number of them that pop up in engineering when I teach it. You're trying to build a bridge and yet it produces an equation that's not solvable by anybody. You can solve any equation by just graphing it and cheating. That's amazing. And so here's what you would have done. And it turns out we're thankful. We are indebted to Newton for this. We're indebted to Newton for the trick that's inside this calculator that I'm about to show you today. And so behind the calculate button in Math 111, you said, let's find the zero. And so that's one of the cool things in here. So I say, I want to find this zero. Now watch what it asks. This is really important for today. It says, what's the left boundary? Well, basically it's saying, this is its way of saying which answer are you after? Because maybe it crosses out here somewhere, or maybe over there. Maybe there's more than one zero for this. So I'm going to say my left boundary is 1. You can just type it. So it kind of marks that, puts a little arrow up there at 1. And I can see it's between 1 and 2. So my right boundary it's asking for, I'm going to say that's 2. And now notice it says, give me a guess. Would you agree 1.5 is a pretty good guess? Thanks to the graph, I can actually make a pretty good guess at this. And so I'll make kind of a lousy guess, 1.1. Since that's inside, it's between 1 and 2. 1.1 is a lousy guess. And so notice it takes, think. What did it take? About a second and a half there. And it says, there's your answer, 1.5811388. And it goes forever, but that's whatever, 7 decimal places or whatever it is. And so, we have this machine. Well, today, that's thanks to calculus. That's calculus programmed into your calculator. And that's what I want to show you with the rest of this class is how did it do that? Or what did it do? You are used to, I am used to, we're lazy and we think, well, of course it did it. It's a machine. But somebody had to make this machine. And that's what I want to show you today. We're actually indebted to calculus for that button, which is why this calculator costs $100. After calculus, you should think, man, this thing should cost $1,000. Because that's a lot of knowledge for free. You were actually getting the use of calculus back in Math 111 and you didn't know it. How does that work? Well, it's actually really simple. You actually already understand from linear approximation that we talked about last week. You actually already understand the math that I'm going to show you here, but you just don't know this particular application for it. So watch this in action. So, final section, God be praised. Newton's method. I can show you how to do this in 5 minutes, but I want to show you where it comes from so that you understand the logic behind it and how it's so simple. Actually, I think I'll tell you. Nah, I'll do it later. So let's consider this equation. Would you agree that's weird looking? Like you, in a sense, don't even really have a sense of what that might look like. It's who knows what that looks like. Well, I'm going to go to Desmos and graph it. Look at that. It's already there waiting for us. And so when I back out a little bit, notice it's like, oh, that's a really interesting graph. It's like almost like a straight line over here, like a 45-degree angle. It looks like a straight line. That's kind of weird. And then it gets up near 0 and kind of does a sharp curve. And then it takes off again. It almost looks like a road, like a long straight road that just has a curve in it. And if I decide for whatever reason, I'm interested to see where that crosses the x-axis there, then notice I can see, and again, Desmos is even better than your graphing calculator because notice it just kind of intuitively knows, like I didn't have to do this left boundary nonsense. It actually kind of puts a gray dot there and you can just click on it. So there's the right answer. Again, I don't need calculus for this thanks to the technology in which we live. I wonder, like if I go back in time with Desmos and I'm explaining this to Newton, I just think that's amazing. Like he had to be a sort of a genius to figure this out, and we can be kind of idiots thanks to calculus being built into all this. But again, the question is like, how did it find it? I don't know about you, but I just have a sense of like, I don't know, I clicked on it and there it was. It seems like, what's so hard about that? But it's like there has to be an equation or some kind of math inside this, and that's the thing I want you to see. So let's steal this graph and take it into our notes and start writing on it, and I will show you the simplicity of this amazing idea. this brilliant but really simple idea that Newton had. So here's Newton's idea. It starts with a guess. I will call it guess 1. And we're going to say that guess is x is 1. Would you agree that's a terrible guess? Because I have a graph, I'm saying I think it crosses right there. Again, did Newton have a
I
graph?
don't know,
of
it seems
this?
good to me.
Newton didn't have a graph of this. So, and you can appreciate how hard it is to make a graph like this. Again, we get one for free and we're lazy and we don't realize how powerful that is. So for Newton to find it, he sort of had to take a guess. And so this is a pretty terrible guess thanks to the graph, but watch how quickly Newton's method will take us to the right answer, which we saw a second ago was 0.567. I wish I'd copied this with the answer on there, but I choked. I think I'll write it in right here. Wasn't it 0.567? Was that what it was? And so we have this first guess 1. Well, here's what Newton said. He said, okay, well, if you go up to this point up here on the graph, so that'd be the y coordinate. Notice it seems to be above 3.5. So here's what Newton said. If you take that point and you do what we did the other day, which is you find a slope, you find a got in my way. That looks reasonable. So that's the tangent line at that point. So let's go get that. You know how to get that. So you say, okay, well, to get that, I know the x coordinate is 1, but what's the y coordinate? Well, I got to plug 1 into my equation. So that'd be e to the 1 plus 1. E is like 2.72. So if I add 1 to that, I get 3.72. So that means the coordinates of that point up there are 1, 3.72. And then, as you know, I got to go get the slope. Well, let's see, what's the derivative of this? If the equation itself is f of x equals e to the x. Notice this is an easy derivative to take. Let's see, the derivative of e to the x is e to the x, and the derivative of x is 1. So there's the derivative equation. So now I can go down here and find the slope. Again, this should all be things where you're going, oh yeah, I've done that before. Oops, that's not right. I'm going to be blue. F prime of 1 would be, well, e to the 1 plus 1, which is also 3.72 coincidentally. So the slope is also 3.72. And so would you agree that if I'm armed with the slope and with the point, then it's not going to be hard for me to find the equation of that line? So I would say, okay, the line then would be y equals the slope times x plus b. And I would put in x is 1 and y is 3.72. And that gives me 3.72 equals 3.72. So that means b is actually equal to 0. So my first equation, that line that I found up there, this is its equation. Would you agree with that? So again, are you thinking, does that agree with the red graph? What about that red graph is like, hey, I must have got that right.
It crosses through 0, 0.
Yeah, isn't the y-intercept 0? Now, does mine cross through 0, 0? No, because I was just estimating, but it's like it's close. So that means my red line isn't terrible. Now, you should be thinking, yes, I understand that math because we did that before, but what does this even have to do with what you're talking about? Like, what does this have to do with finding a 0? Well, where this hits right here, that just produced your second guess. That's an improved guess that you just got right there. So if you follow that tangent line down to where it hits the x-axis, now you just took your crappy guess of 1 and you just improved it to 0. Now notice it's not great yet, but watch how fast it gets great. Now, how do you algebraically find that? Well, remember that the 0 is sort of code for y equals 0. So if I throw 0 into that, then I get x equals 0. So effectively then, you just landed at guess number 2, which is x is 0. So there's your first guess. There's your improved guess. Come here, Aspen.
There's Grand Doug. There's Grand Doug.
Hi.
There's Grand Doug. Look at all
Say
those
hi to my
people.
friends. These
Look
are
at
my
those
friends.
people.
Say hi to them.
I can't.
What do you think about those friends?
I can't.
Hi. Wait, Tim. You want to write for him?
Yeah.
Right on there for him. See?
Uh-oh.
Uh-oh.
Can we off?
Can you do it off? Do you need to get rid of it?
Yeah.
You just erase it like that.
How about that one?
You write one more thing for him and then we'll. Oh yeah, that helped him. Is that helping? You guys get that? Is that good?
It all makes sense now.
Yeah, crystal clear.
Yeah. Mhm. All right, I got to teach him. After class is over, you can play on that if you want to. Oh yes. So now what you do is just repeat the process. What did we do? We said, okay, well, let's do this. Let's just start over. Let's pretend our guess was 0. What did we just do? There's nothing else to say here. I just have to repeat the process. So I say, okay, well, that just took me to that point. And now here's where Newton's method starts to get really brilliant. So let's do another graph now that's tangent to that. Would you agree that looks pretty good? And do you see where this is going? Because what happens now, well, that right there is my third guess. Do you see how that's taking me to the right answer to this question? Newton's method is. So that third guess I'm about to get by doing this process over again is going to get me pretty close to the answer. And then one more guess and I'm pretty much going to be there. And it just involves getting there by use of calculus and a tangent line. So that line is progressively just pointing closer and closer. So let's walk through that again. I guess I can't leave all of that stuff, can I? Sorry, Aspen. So let's see, what did I do now? Let's go back and kind of start over. What did we do? Well, we said we had to find the coordinates of the point. So we have to put 0 into our original equation. Our original equation was e to the x plus x. E to the x plus x. E to the 0 is actually 1 though, so this is 1. So that means I have the point 0, 1. In other words, that's where it hits. And notice that did hit at 0, 1, didn't it? That's where that green point was, 0, 1, cool. And now I need the slope. Since the slope equation was e to the x plus 1, e to the 0 is 1, 1 plus 1 is 2. And so here's my point, here's my slope. So my equation is y equals 2x plus, what's my y-intercept? Well, when x is 0, y has to be 1. So that means this has got to be 1. Isn't that my equation? So there's my tangent line. And what was it I did to that? What was the logic? What did I do with that blue tangent line there? What was my goal? What did I use it for?
Shouldn't that be -1, not +1?
Did I get it wrong? Actually, let's check my graph. No, because wouldn't my graph cross up here at like 1? Isn't the y-intercept graph around 1?
Right, I had the x and y intercept swapped in my head.
Yeah, good. I love it. Speak up. Let's think, let's reason, let's make sure. What good is that tangent line? What am I doing with it? How do I get that guess 3? What do I do algebraically to get guess 3 there?
Don't you plug in y equals 0?
Yeah, y is 0. And notice I'm, if you will, too dumb to solve this green equation for y is 0. If I wasn't too dumb to do that, then I wouldn't be doing this. Like if I put 0 in for that, I can't solve that. There's an e to the x and an x. You can't solve that algebraically. There's not a way to find that, but I'm doing it with a line. I'm approximating my equation with a line. That's what we did before. We approximated a complicated graph with just a line, and that's what we're doing again. So now, y equals 0. So I end up with 2x plus 1 equals 0. I subtract 1, and x is negative 1/2. And so I just arrived at guess 3, which is x equals negative 1/2. So that's better. Remember, the answer to this was negative 0.567, and we're already at negative 1/2. Notice my red dot there is about at negative 1/2, but I didn't draw it perfectly. It was just an estimate. Negative 1/2 is actually right on that mark right there. So that answer is already accurate to the 10th place. And notice I started with a terrible guess. I started with a guess of 1, which is not even in the vicinity.
I have a question.
Yep.
Could you use this on cubed graphs?
Yep.
And
You can use it on any graph. That's what's amazing about it. You can use it on any equation. As long as you can take its derivative, then this technique will work. And that's what's programmed into your calculator. So again, you're used to thinking of things like magic, like you flush your toilet and it's just gone, or you plug your hairdryer into the wall and it just starts. But it's like, that's not magic. There's a reason behind that, and it's smart people working hard that's behind it. And so it's kind of cool to understand that. This is what's behind that button in your calculator. Let's do one more step. See. So what'd you do? Don't be a curmudgeon? What? Did you teach her to call me a curmudgeon?
No, I said, don't be a curmudgeon. We saw
Don't
all
be a
these
curmudgeon.
unfriendly people and I told her because we're curmudgeons.
Don't be unfriendly. Don't be a curmudgeon.
Always be friendly.
Bye-bye. See you later. Thanks for coming to say hi today. So let's see, what is e to the negative 1/2 plus negative 1/2? My magic machine. Notice I can't do that in my head anymore, so I've got to kind of cheat and figure that out. E raised to the negative 0.5.
but Newton didn't have calculators.
I know. And remember what I taught you last time. How did Newton figure out e to the negative 1/2? Well, he approximated it using the same exact math. So this is just crazy, like the world that we live in. So yeah, isn't that funny? Like, and if you will, when I was a kid, we had calculators that would tell us e to the 1/2, but we didn't have graphing calculators. And so in a sense,
So
that's what I'm doing right now.
We're approximating an approximation.
Right. Yeah. But it's better than like having no answer at all. Because remember, as I mentioned, equations you can't solve come up as a result of algebra, or come up as a result of engineering. Like I'm trying to build a bridge and I end up with an equation I can't solve. So if you can get an approximation somehow, even if it involves a slide rule and, you know, spends hours, you know, doing long division and all this nasty stuff, like it's cool that you can actually at least get an answer, even though it's terrible. So let's see, I got 0.1065 for that. So that means I have the ordered pair. There's my ordered pair. Now I got to go get the slope. This is the last time we're going to do this. So now I stick that same expression into my derivative equation, which was the same thing except it was +1. And I got 1.6065 for that. So I now have everything I need. I have the slope and I have a point. So that means my equation is y equals 1.6065 times x plus, and I want you to watch this carefully because all I'm going to do after this is just show you a shortcut to do this faster. So what do I do to get that b value right there? I'm trying to figure out what b is, the y-intercept. And so don't I plug my y value in of 0.1065, and then to get b by itself, don't I subtract this to the other side? So it'd be minus 1.6065 times x, which is negative a half. Isn't that what I do to get b? So my calculator says 0.1065 minus 1.6065 times negative a half is 0.9090975, and so I found my equation. And then lastly, I put 0 in for y, so to solve for x would be subtracting this to the other side. And then I would divide both sides by 1.6065, and that'd be my x. That would be guess number 4. Do you agree with that? I'm typing that into my calculator, and so I'm changing colors. So if I take negative 0.90975 divided by 1.6065. Wow, what an amazing answer. Guess 4 is negative 0.566. Man, that's amazing. That's actually, that's 1/1000th off of the correct answer. I'll erase this because it's going to get confusing, but what did we just do? We went to this point right here. What are we doing? What's going on? We went to this point right here. Why do you keep moving? We went to that point right there, and can you appreciate that this next tangent line is going to be just hitting the green point almost exactly? You see how that works? Now, you should understand that this process never ends. Like, you could just keep going and going and going and just get closer and closer and closer and closer. But does it make sense if we're not going to do this, but if we did it one more time, does it make sense our next answer is going to be really close to the answer we just got? Like, that's how you tell you're getting there. You keep getting the same answer every time. When you get the same answer every time, you can stop. Now, what I'd like you to stare at now is the shortcut to this. We're trying to speed this up. And so if you look in your book or you look on the note sheet that I gave you, this is not the method that I use because we can speed this up. Did we actually ever need the line, the equation of the line? No, we needed the line to set it equal to 0 and solve it. So what I want to do is try to think about, I want you to go back and think about where these things came from. Like this. Where did that come from? What did we do? Keep in mind, when we started this last push, we started, if you will, with x equals negative 1/2, and it resulted in 0.566. And so what we need to do is, like, is there some way we can skip, like, what can we skip of all that algebra that we did in there to get this answer? Well, think about the 0.90975. Where did it come from? Think about the 1.6065. Where did it come from? Because that's all we needed, right? We just need these two numbers at the end here.
Could you build an overall equation?
Yeah, that's exactly what we're trying to do. We're trying to find. Now, Newton's methods does require you to go step 1, step 2, step 3, step 4. There's not a way just to go immediately to the right answer. You can't stick one in and it just pops out the right answer. But it steps through, and this is what computers are good at and why somebody programmed your calculator to do it. Well, let's think about this statement right here. Let's copy it down. Where did that come from? Well, wasn't that just, let's see, back up here, 1.106. Wasn't that, oh, that was this number right here. So that number is the slope evaluated at the guess. Do you agree with that? So that's the slope. That number came from the slope being evaluated at our previous guess. Isn't that where that came from? Do you agree with that? What about this 0.90975? Where did it come from? Well, wasn't that, let's see.
Well, we needed to use our x point, plug it into our y equation to find the b.
That's right. In
using
other
this.
words, didn't it come from right here? So to get 0.90975, we had to take 0.16. Let me see. I'm just trying to give you time to think about this. I obviously already know how to do it, but didn't we have to take the 0.1065? What was 0.1065?
The Y value.
That was the y value, wasn't it? 0.1065 minus 1.6065 times -1/2. Wasn't that the y value? So that was f of -1/2. That was the y value. And wasn't that the slope? That's the same slope we had just a minute ago. So that's f prime of our -1/2. And then that actually is -1/2. Like we don't actually have to have the line. Do you see what I'm saying? We're just trying to speed the process up. So let's think about what that is. So if we wanted then, since that problem was guess number 4, if I say if we want x number 4, and I'll go back and write this right here, and if this was x3 back here, that was our third one. And so how do we go from one to the next? That's what I'm getting at. So let's see if we can write out what that says. So to get x4, then we actually took the numerator, which was, let's see, this statement, except for instead of saying x -1/2, I'm going to say x3. And then it was minus f prime of that value, that was this right here, multiplied by the value itself. Isn't that right? Now, that gave us this number, which was positive, but why was it negative down here?
Because we had to subtract the bigger number from the smaller number.
Yeah, we had to subtract it over to the other side, if you will, to get that answer. So we subtracted it over to this side, basically. So it ended up changing the sign of it. So notice we got a b value of positive 0.909, but in the answer, in our x, it was actually negative. So that means I actually have to kind of multiply this whole thing by a negative. And then the denominator was, well, just this back here. It was f prime of our value. So if you will, this is a recipe for how to get from one value to the next. Let's think about that a little bit more. Let's clean that mess up a little bit. Again, what we're trying to do is automate this. And in your world, that's been automated to the place where you didn't even know it existed. It's like sitting inside your calculator, you didn't even know it. So let's see, what is that equal to? Well, let's even take it to another notch. Let's even say this. If this next term here. So I'm going to kind of think of this as our next term, and this is our previous term. So whatever term you're at, this is how you get your next term. Would you agree that since everything up here is divided by this derivative, then I can say, well, that'd be negative f of x3, or I'm going to call it xn, divided by f prime of xn. That's this divided by this. And then it's also this divided by, but then it's minus a minus. So this becomes actually a plus sign now. That's f prime of my previous term times my previous term divided by the derivative of my previous term. Hey, that's cool. Look what happens. I can cancel this out. And so Newton's method, and this is what's written in your book, and this is all you see in the book. You go into the book and this is what you see, and it just looks like magic. If you want the next term, what do you do? Well, there's a minus sign here, so I'm going to put that. I'm going to just take this sign and put it first. You take your previous term and you subtract from that the function evaluated at your previous term divided by the derivative evaluated at your previous term. This is actually Newton's method. It's what we just did, but it's automated now. We have a formula. You don't even see the line anymore. You don't even really see what it's accomplishing. That's faster.
I kind of Newton because being like so far back, like trying to explain this to like colleagues and stuff, it'd be impossible. Like
Yeah.
trying to teach other people, you know, your ideas.
Yeah. And the amazing thing about, you know, reading a little bit of history about this is at some point, Newton is in his ivory tower or wherever he is, figures this out, and he's like wants to communicate with some other mathematicians in the world. And, you know, it's just kind of what I was getting at before. It's like, how are you going to write all that down? And even the concept of how you wrote algebra wasn't the same. Incidentally, both Newton and Leibniz invented calculus, but they had totally different systems for what a derivative was, what they called derivative. Prime was actually Leibniz's idea. Newton's was this. For him, f prime was like a dot over it, and the second derivative was 2 dots. That's what he called the derivative. And so they had different language for even how they communicated about it, which is kind of interesting, I think. Well, let's just try to use this. Let's try to use this, and let's use it on the previous problem just so we can watch it working. So, okay. So we said our first guess was equal to 1, right? And that was our terrible guess. And so how do we get x2? According to this, we say, well, the next guess is found by taking the previous guess, which is 1, minus the function evaluated at 1, which we said was 3.78, if I remember right. No, 3.2, forgot. 3.72. Divided by the derivative evaluated at that guess. And this one coincidentally was the exact same number. And so you end up with 1 minus 1, you get 0. So there's your next guess. All right, your third guess. You take your previous guess 0 minus the function evaluated at 0 divided by the derivative evaluated at 0. The function evaluated at 0 was 1. I forgot. Is that right? The function evaluated at 0 was 1, and the derivative evaluated at 0 was 2. So 0 minus 1 divided by 2. Oh, that's negative a half. You see your guesses progressing? It went from a terrible guess of 1 to a better guess of 0 to a better guess of 1/2. And let's do one more step. To x4 is, what do? Your previous guess minus the function evaluated at that previous guess divided by the derivative evaluated at that previous guess. I forgot the decimals for these. 0.1065 and 1.6065. And that's what produced x4 is approximately 0.566, except for I think that was negative. So there's our fourth guess. I mean, that's pretty cool. So you didn't have to stop to find the equation of the line. Well, let's test this out. Like, let's say on a cubed equation now, just like to get a chance to figure this out a little bit better. Let's go back and let's go make a cubed equation. So again, I'm kind of making this up. I am totally making this up randomly. Minus 2x squared plus 5x minus 9. So again, we have the advantage of looking at and notice from your algebra knowledge, the cubed equation has 3 answers. So apparently this only has one real one and the other 2 are imaginary. And so would you agree it crosses out around 2? So let's say we started with a guess of 0, which is a terrible guess. You agree with that? So I'm going to start with a terrible guess of, so kind of memorize that. Notice it's a hair short of 2. Maybe I'll bring the graph in later. Oops, I forgot the equation. One, negative 2, 5, negative 9. Negative 2, 5, negative 9. Was that it? So we're looking for
I think
a
it's minus
0.
9 at the end.
What's that?
Yeah, I think it is too.
What's wrong?
I think it's minus 9.
It's minus 9. I have a really bad memory, so yeah, it was minus 9. You're right. And so I make my first guess, x equals 0. Notice if I'm Newton, I have no idea what to guess here. Remember, he doesn't look at a graph of this. So let's record, we're going to need a derivative, so let's record it over here. The derivative of that is 3x squared minus 4x plus 5. Come on, plan ahead, man. And so I want you to notice something here that's kind of important, and that is this. Watch what happens when so your guess is stupidly 0, like you have no idea whether it makes any sense at all. So then you plug in 0 for x, and maybe it would make more sense to call this f of x. And you get negative 9. Does it make sense? That tells you right there how bad your guess is.
Yeah, because shouldn't it be closer to 0?
Should be close to 0. So notice if you're Newton and you want to make a good guess, couldn't you try some other stuff like, I wonder what f of 1 is. And to save a little time, I'm going to type this in my graphing calculator so that I can get these answers without working so hard. Plus 5x minus 9. So if I hit graph and I say and I trace, I'm just using my calculator to steal this for me. If I hit trace and I stick in 1, I get negative 5. Notice how that's better. Hey, I'm closer to 0. I think I see a pattern. I think I must be going this way. So then I go to 2, and then I get 1. Do you see how it transitioned from negative to positive? Does it make sense? It must have crossed the x-axis between there. Do you see how you could actually make an intelligent guess? So 2 is 0 is a terrible guess. Armed with this information, I'd be starting with 2. Do you see what I'm saying? But let's just start with a terrible guess just to watch it work. So I also need f prime of 0, which is, of course, 5. And so now I have everything I need. So if that's my x1 guess, is 0. Now let's go get the x2 guess. How do you find it? What did Newton say? It says take the previous guess and subtract from it the function evaluated at 0 divided by the derivative evaluated at 0. So for me, that would be 0 minus -9/5. So that's 9/5. So there's my second guess.
That's crazy. It only takes 2 repetitions of this to get the answer to 3 significant digits.
It's
Crazy.
ridiculous. 9/5. That's 1.8. Remember the graph? What's the right answer? It's already, even starting with a terrible guess, it's already accurate to a 10th. So let's go find the next guess. All right, well, how do you get x3? X3 would be the previous guess, 9/5, minus the function evaluated at 9/5 divided by the derivative evaluated at 9/5. So the function evaluated at 9/5 is -0.648. And the derivative evaluated at 9/5 is 7.52. So I just need to type 9 divided by 5 minus a -0.648 divided by 7.52. I got 1.886. So just for comparison, back here, this was 1.8. Can you tell I'm honing in on it? Do you see how this answer wasn't that different than the previous answer? I got 1.8, now I'm at 1.866. Let's do this one more step, because remember, we have a graph, and so we already kind of know this answer is right, but let's do it one more. What's the fourth answer? It's 1.886 minus, I'm gonna save a little time, and I'll write it down. F of 1.886 divided by f prime of 1.886. What is the function evaluated at 1.886? It's 0.0245. Do you see how you can already tell you're getting there? Because see what the function is evaluated at? When you stick in 1.886, you almost get 0, you get 0.02. And what happens if I find the derivative? Well, I get 8.1, about 8.127. So, all right, what's my fourth guess then? Well, if I evaluate that, 1.886 minus 0.0245 divided by 8.127, I get 1.88298. Do you see how close these two answers are? Do you see how that kind of tells me I could say I'm done now if I had no reason to be more accurate than this? I'm really honing in on it. I'm close now. So 1.88298. What does Desmos think the answer is? Notice how I'm already accurate. I'm within 1/10,000th of that answer right there because I got 1.8829. That's kind of cool. That's what's programmed into your calculator. Does that make sense? It's an iterative process. And if you know anything about computers, and I'm actually going to show you how to do this in Excel here in just a second, but if you know anything about computers, what you'd have to, how do you decide you're done? Because how does it know when to quit this process? Well, what you do is you just check to see is x4 minus x3 less than, say, 0.01. In other words, you say, I'm going to quit. If I'm accurate to the 10th place, that's good enough for me. So you'd write a little routine or just write a little if statement that said, not is, if. You'd write the statement, if this is true, then just tell me the answer. Tell me x4, because that means I'm close enough. If it's not, then go repeat the process again. So on a test, that's what I'd want to see. And you want to look at your graph because all you have to do is type one number in wrong or, lose a negative sign. I mean, you're still doing a lot of math and it's easy to accidentally do something like this. But the main thing I'd be checking on a test is if you started with this and then you got this and then you got this and then you got that, then I would kind of know, oh, look, I see their progression and they're working their way toward the answer. I don't want you to do this, 10 times. That's too time consuming. But it's fairly straightforward. So your note sheet for the test has just that formula right there. It just says Newton's method. There you go. And notice it's cool. It involves a derivative. So that's a neat use. Now, what I'd like to show you is that same process, except for I'm going to do this with Excel now. I'm going to do that same process, but let's get computers involved. You don't have to do this by hand. And so you don't need to know this as far as this class is concerned, but I just think in the world that you live in, it's kind of unfortunate. And I think this will help you see how there is a routine in your calculator to bring this about. So let's see, what were my ingredients? So I had my guess, and then I had the function evaluated at that guess, and then I had the derivative evaluated at that guess. Like I'm just making notes to myself. And so let's see, my first guess on that was the lousy guess of 0. Is that right? I'm looking back at what I wrote. Yeah, 0. So my first guess was 0. And then what did we do? What did we do to get we plugged the value into the equation. So have you seen Excel before? What do you do to plug the value in? Well, you say this cell will equal, this is how you say this in Excel, this cell will equal, and wasn't our equation x cubed? And so I'd say equals, well, this cell, whatever's in this cell, cubed.
Are you meaning to share your screen?
Thank you. I have not shared my screen. You're not seeing this. That is regrettable.
I was so confused.
No kidding. It made no sense at all what I was just saying. So let's start over. So I just made labels for myself. Let's make those red and bold and underline them. And so my first guess was literally the number 0. And then what did I do to figure out what the equation said when I plugged 0 in? Well, the equation was that number cubed. So I said equals C4 cubed. Cell C4 is where that number is located. And then the equation said minus 2x squared. So then I go on and say minus 2. And I think in Excel, you actually have to say times. I don't think you can leave that off. You can't just say 2 times C4 squared. So, and you can just type C4. So it was minus 2x squared, and then it was plus 5x. So if I say plus 5, and this is what you can't do. You can't just say C4. It doesn't know that means multiply. So you actually got to say multiplied. And then it was minus 9. And so is this working? Yeah, that gave us minus 9. And then we also had to plug in this value into its derivative. And so the derivative was equals 3x squared, 3 times C4 squared. And then it was minus 4x, so minus 4 times C4. And then it was plus 5. So isn't that what we got for the values before? Again, I don't want you to actually, I'm not showing you this slowly enough for you to totally understand it because we're running out of time, but I just want you to watch the process and how cool it is. And so then what do I do to get my next guess? Don't I take equals my previous guess, this is what Newton's method said, right? Minus the function evaluated at that guess divided by the derivative evaluated at that guess. Wasn't that our next answer? Now here's where computers get cool because I'm now done. What do I have to do? Well, all I have to do is take these two formulas and copy them down. Wasn't that our next two numbers? And not only do I need to do that, I just need to copy the whole thing down. There's our next guess, 1.88617. If I copy it down one more time, there's our next guess. Notice how close those are. If I copy it down another time, notice it only changed by, what is that, 5 tenths, hundredths, thousandths, 10,000, it changed by 5 millionths. So I'm pretty much there after only 4 steps. So those of you that are kind of computer programming minded, maybe you can see the value of this. So that's pretty powerful. It's a pretty quick result to the answer. So notice what I see here happening is these answers are all pretty close to each other. That's how I know I'm getting close to the answer. And I see these numbers getting closer and closer to 0. Do you see these last two as scientific notation for 0? That's 7.63 with the decimal point moved 11 places to the left. I mean, that's a really small number. And then I'm seeing the slope being the same. So you can copy a whole bunch of them down. Notice there's no change at all now. Like you were done a long time ago. You don't need to do this 12 times. You were done after 5 times. Let me quickly go back and redo the original problem. The original problem said our function was e, which is in the language of Excel, you have to say exp. It was the number evaluated e to that number plus that number again. Wasn't that our equation? And the derivative was the same thing, except for it was the function evaluated at that number, but then it was plus 1. And so there's the answer. Again, I did it 12 times, which apparently I didn't need to do. So what if you started your guess at worse at like 8? Notice how it still takes us there, but it takes us a little longer because your guess was so terrible. See how terrible it was when you put 8 in? Did you get 0? No, you got 3,000. Your guess is so far from 0. That's the worst guess ever. And yet notice it only took still like 10 steps to get the right answer. I mean, that's really, really cool. That's why your calculator has that trick built into it. It's kind of neat. So I want to be able to ask you a question on a test like this and have you show me a few steps. But you can use your graphing calculator so you can at least tell if you're getting it right. You should know if your answer is right. Use Desmos or use the graphing calculator to kind of tell whether it's working or not. All right, I need to shut up. You guys owe me a quiz today because I'm going to grade that in time. And there's nothing, this topic wasn't on that quiz. You may have other things going on in your life and be behind, but you should already be done with your quiz. You should be done because I taught you all that stuff before, and if you're keeping track of the class. If you can, I put a due date on it for today at 1 because I want to have time to grade it. I think I'll go in and cut you some slack and make it later. But if you give it to me too late, I won't have it graded for tomorrow. So I'm going to start grading those this afternoon. And ideally, again, I give you that graded quiz back. You learn from your mistakes so that you can ace the test. That's what we're all after, is you getting an A in this class. So that quiz does you 0 good if you don't get it back graded before you take the test. So I hope you're done or really close to being done. Got to help my son-in-law, that girl's dad, tonight do something, so I'm not going to be around a whole bunch tonight. So that's the plan. Then tomorrow, you've already got a review in my open math, which is an assignment. But you've got a review in there. I don't have any plan for tomorrow except for just to get together and maybe make a couple comments about the quiz in terms of teaching you some things, make a couple comments about the review, mainly just answer questions. And I guess the thing I'd be concerned with is, can you stare at my note sheet and, do the test? Because now you got to think, can I do everything we've done in this section? So anyway, that's what's left. And then Turkey Day. You don't have to do anything over the weekend, 4 days in a row. That's awesome. Eve?
So the test on Wednesday is for chapter 4. And then do we have like a final the next week?
Yep, there's a final next week. And again, I'll have a review for that. And I want to narrow down, like we've done a lot of things. The final exam should feel pretty overwhelming to you. but there's a lot of things that aren't super important. So, I want to make sure I tell you what things are really important and, give you a chance to practice them and so forth. And again, that's, you have my note sheet for that test. So you don't need to remember that the derivative of sine is cosine or the derivative of tangent is secant squared. You should not, that should be like, God, I did know that once, like it was another lifetime. So that's like chapter 3. It feels like a lifetime ago. So you have that note sheet to look some things up. So the main thing is for the test is, can you take the derivative of stuff when there's product rule, quotient rule, and chain rule involved? So can you take the derivative of reasonable expressions? I'm not going to give you really hard questions. I want this test to be, the final to be a celebration of the fact that you have learned those things. And those are on your sheet. Like, what's the product rule? Oh yeah, it's on there for my sheet. It's on my note sheet. And then, can you do some of the cooler, more straightforward applications? Related rates was a cool one. And then this REITs and stuff where you maximize things. Those are kind of neat applications of derivatives. So, and in my opinion, like, you should not see any questions on the test, on the final, that you haven't already seen before. I don't mean the exact same question, but the same type of question. So if you look back over your test and you look over the review that I gave you and you feel good about that, then you'll do great on the final. So yeah, there's nothing new to learn. We're now done learning. You just have to kind of show the world you actually learned something in this class. And there's kind of a bunch of time to kind of process and think about that. So test on Wednesday, and then I've got a couple of projects that should help you get smarter for the test in a sense. We'll do a couple of projects a week from today and Tuesday, and then we'll review for the test at the end. So take a look at your syllabus. All right, I've held you way too long. Get out of here or stay after. You're more than welcome to ask me any quiz questions. Did I get this question right? I'm stuck on this question. Stay after and ask me those questions.
See you tomorrow.